Well, thank you, Peter, for this very nice introduction. And I also would like to thank Yangjin and his collaborators for organizing a perfect meeting. I came to 5 or 6 of this circuit, and I started to look at them as some kind of family reunion. So it's always great fun to go to such events. So my collaborators are Jack Krzyzewski from Cross Cancer Institute at the University of Alberta in Edmonton, and Ed Riedman from Cancer Systems Biology Center at Tufts University. Jack is a physicist, and he's very much interested in rational drug design, and they have large supercomputers, and they do a lot of molecular simulation at the molecule level, trying to match drugs into their targets. Some of you who were at the meeting a couple of years ago may remember that Jim talked there. And so what I want to talk about are, first of all, networks in general, and I'll specify to molecular pathway networks and protein-protein interaction networks. Then I'll introduce two descriptive quantities, automorphism group sizes and cyclospaces and cyclomatic numbers, and we'll see how these quantities correlate with survival statistics. And then I'll discuss these results a little bit and try to point out to future research. So here are two pictures of networks, actually quite old pictures. This is a picture of the Internet connectivity graph from about 15 years ago, and this is the Algebraic collaboration graph from 35 years ago, and obviously we all know where we are, somewhere on this periphery. And the interesting thing is that many of these networks share similarities, which you would not expect because of their very different nature. And so people have been asking what are the design principles, if you can call it like that, of these networks. Of course, they're not really designed. People start to work with each other on by chance, but still there are some sort of similarities between these types of networks that one would not.
What does it send every 100 net?
Oh, I have no idea. I mean, this is just, something that I downloaded from the internet. That's how it, I think this is at the IP level, so, but no particular reason. So, yeah? Oh, the NSA, yeah, that's somewhere in Maryland where, they sit. Yeah. Okay, so here, this line of research was instigated by physicists, by Albert Barabashi and his co-workers about 15 years ago. And what people did was to plot the degree distributions of such networks. They called them scale-free networks, or also hierarchical networks. And it was discovered that over large stretches of degrees, so several orders of magnitude, they observed this typical power law decay of the degree distribution. This is taken as a signature of organization in some way or another versus a completely random method. So the reason for that is, of course, depends on the type of the network and the origin where it comes from. But generally, engineered networks, they should be somewhat safe to failure of a node or a link. You don't want to have one link failing and the whole thing falls apart. And so at the organization level, you often observe that there are small communities which are tightly connected internally and loosely connected to one another. And as I said, the typical sign of design or organization are so-called fat tail distributed. Now there are all people who criticize this, or especially if it's over a short range of degrees. So if the degrees range from 1 to 15, and you plot it on a log-log scale, of course everything will be a straight line. But still, there's a, if you have a longer range of degrees, then you can also expect this power law to decay. So now I'm going to talk about protein-protein interaction networks. Those were taken from the Kyoto Encyclopedia of Genes and Genome. And here's a picture that I think is a cell. This is the plasma membrane, and this is the nucleus. And the nodes, it's very difficult to see here, but this one is, I think, then here is P53, which is probably too small to see. But those are proteins, and these proteins interact with one another with pointed or with blunt arrows, and they're also localized in different regions of the cell. And many years of publications went into such a picture to come up with this interaction network. And now we're going to look at this from a very abstract point of view of mathematics. So we're just thinking of this as undirected graphs where the vertices are in proteins and the vertices are connected by an edge if and only if there is a known interaction between these proteins. And there are different types of interactions, but they're all lumped into the same edge between these vertices. So there could be a binding of proteins, or there could be catalysis of a reaction. But for this purpose, we just look at graphs with edges between protein nodes. And there are different bioinformatics toolkits that are open source and can be downloaded from these websites, which just allow to extract these networks from this tech database. And the way a mathematician looks at this is a table of proteins with two columns, and the two partners in the interaction are in these two columns. So this is the data that we are looking at. And is there anybody who's not a mathematician left in the room? Not that anybody? Or, well, you are a mathematician, right? No, it's just that because some people on the first and on the second day were, one guy said that he became a biologist because he hated mathematics. I did not take this well. Okay, so I don't need to explain what a permutation is, right? So automorphism is just a permutation of the vertex set, which preserves the adjacency relation. And it's a very easy exercise to show that these automorphisms from a group with respect to composition. And we are looking for evidence of network organization in this automorphism group of the graph. And here's a very well-known model for random graphs, the so-called Algebraic graph, where you have a certain number of vertices, and every edge is present with a certain probability independent from all the other edges. And then it was shown by about 35 years ago that in the limit of large vertex sets, these Algebraic graphs are almost surely rigid. In other words, they have none other than the trivial automorphism. So there's very little symmetry. In fact, this goes down exponentially in purely random graphs. So in real-world networks, the situation is vastly different. This is a paper by Ben MacArthur, which appeared a couple of years ago, where they looked at different biological networks and technological networks and determined their automorphism groups. And so here you have this column the number of vertices, here the number of edges, and here the size of the automorphism group. And for example, in the case of the internet, the this is a decomposition of the automorphism group into factors, symmetry groups.
What is M in that? What is the second column?
This is the number of edges. I don't know, maybe this is up to 10, up to a certain factor. So this is the number of vertices, this is the number of edges, and this is the number of automorphisms. And obviously this is far from being an Erdős-Rényi graph, which is not surprising. You know, these are just. I mean, this is. Well, if you go back to this picture, so I mean, whenever you have a star, right? So one central vertex and many edges with a terminal vertex, right? Then you automatically get an Sn with that many vertices, right? And then you have a lot of those, and then that's how you get these big automorphism groups, or these big components. Okay, so here is the protein interaction network of pancreatic cancer, which was mentioned before, and that's relatively small in the sense of it has about 80 or so vertices, and there's an open source package called Saucy, which allows you to find the automorphism group of this network very quickly, and it's this direct product. Yeah, as I just mentioned, so when you have such a tree-like structure at one end, then that gives you an S body. There are two of them here. So I'll come back to this network later. We'll see that the source of symmetry is not only at these tree-like protrusions at the ends. Then when you have different networks or different numbers of vertices, then you want to somehow compare the automorphism group sizes, and the idea that these people have proposed here was to make this relative to the automorphism group of the complete graph on n vertices, which is n factorial, and I don't know exactly why they have this one n here, but so this is just an empirical measure, I would say, to make automorphism groups on different graphs comparable to one another. So this much I want to say about automorphism groups. Well, I'll come back to that. Next, I want to introduce another invariant of the graph, which is more of a topological nature, which is the cycle space dimension. So a cycle is well, basically a sequence of edges that closes on itself, and these cycles, you can make them into a vector space over the field with two elements by taking the symmetric difference as the addition, and the empty cycle as the zero element, and multiplication with one is just the identity. And since this is a vector space, it has a dimension, and this is called the cyclomatic number, and it's not difficult to prove that this is the following alternating sum. It's the number of connected components minus the number of vertices plus the number of edges. So in a way, this looks like an Euler characteristic of this graph, and yeah, so this is called the cyclomatic number. So here's a simple example. Here you have this diamond with one connection, and there are three cycles, and any two of them are linearly independent. So you can think of this as counting linear independent cycles, and in a way you can think of this as a measure for the topological complexity of this graph. So people in computer science have used this as a measure of complexity of programs, where these are loops that the program has to go through. So here are now our two main results, or yeah, the correlation with the survival rate. Survival rate data we got from the surveillance epidemiology end results database, and these are 11 human cancers. Let me go through them. Pancreatic cancer, small cell lung, non-small cell lung. This is acute myelogenous leukemia, glioma, chronic myelogenous leukemia, colon cancer, endometrial cancer, renal cancer, bladder cancer, and thyroid cancer. And there are several things to.
What are the axes?
Yeah, I'll say it more. So this is this 5-year survival probability, and so the fraction of patients that are alive 5 years post-diagnosis. And on the y-axis we plot this relative automorphism group size that I defined on this previous. So we calculated the automorphism groups for all of them, and then calculate this one.
Oh, so the data is from the website, your beta G from your research.
Yes. Yeah.
Okay, you know.
Actually, I have to say this was given to me by Anna, and so here are the 5 years of probability. So several things I want to remark here. So first of all, there's a huge difference in types of cancers, right? So you don't want to have any one of them, but many are way worse than others, right? So pancreatic cancer, small cell lung cancer, those are practically death sentences. And what we find in these data is a clear correlation between the 5-year survival probability and the relative automorphism groups. No, the protein-protein interaction network. Yes. Well, I don't know, but in this case, I would say 70, 80. So they are all not that really big. So 150 is some of them. So and yeah, of course, I have to say. So whatever is in that database is also subject to renewal, update. So these are many hundreds of papers which report this link between whatever KRAS and KRAS and things like that. So this is a lot of this work that went into building these databases.
Can you put up the formula for your beta G?
Yes.
What really beta G tells you on the graph?
Well, it's the amount of symmetry that graph has versus the complete graph. Right? So the complete graph, you can compute any vertices, right? And so it has an factorial.
Does it have any unique negativity?
Well, that's precisely the question, right? So this will be the future research. I'll come to that at the end, okay? So that's one of these correlation pictures, and then we also have a correlation in the other direction, although with the symptomatic number, with the topological complexity of the network. And we made some error bars here because it's really 10% is a conservative estimate, so you don't know exactly about these survival probabilities. You also don't know exactly whether all these protein-protein interaction networks are complete. But still, again, I mean, this is have to bear in mind. These are biological data, right? So these are over hundreds of people or thousands of people, and there's this is not a cloud. I mean, this is correlation. Yes.
In each case, it looks like you could put a quadratic
Yes. Okay, so in fact, that's something that we thought about too. But you know, I mean, as a starter, this is the first paper that we made in this direction, right? So yeah, if you think of this as a measure of symmetry, then greater symmetry in the protein-protein interaction network is associated with better chances of survival. And this is interesting fact. We don't really have an explanation for that right now, but so this will be the topic of future work. And And at the same time, high topological complexity is correlated with a decreased 5-year survival probability. And those p-values are pretty good. I mean, make us confident enough to submit this to the show. So there's a similar correlation result which was obtained by a student of Jack and Ed, and that published about 2 years ago. And there they looked at the degree entropy of a graph, which is this expression here. You multiply the degree with its logarithm and sum it up over all vertices. And again, you have this very clear correlation. If you take entropy as a measure of disorder, then again, a higher amount of disorder in that network is detrimental, and a greater order or lesser entropy in that network is a better sign. Again, within all the parameters, this 5-year survival probability. So I have to say, these databases, they don't contain anything else. So they don't contain the stage of detection or the treatment or the general health of the patient or the metastasis status. So those are very, very coarse databases, but still they're also very large, and so you have a certain confidence in these survival numbers. So here's another picture of the same pancreatic cancer network that I showed you earlier. So here I have highlighted in yellow certain orbits under this automorphism group, and the surprising, what I found a little bit surprising, is that some of these proteins, they have a high degree of connection. So this is degree 3, this is degree 4, and this is degree 8. And if you look at now at these labels, so they are known. So these are the PIK3 kinases. This is, I don't know what this really stands for, 88P1 and P3, but it's also very well known and well-studied set of proteins. And here we have VEGF, which was mentioned. There are several types of VEGF. And yeah, so if you think of this as some kind of social, quote-unquote, network, and flow of information between, for example, this node and this node, it has 5 routes how it can go from here to here. Right? So they are all interchangeable. And so, in other words, knocking out one of them would help almost nothing, because it would still be able to go around these corners. So this is part of what we see in here. What would be optimal drug targets if what you want to do is to destroy the network somehow? Or I'll go to that next slide. So yeah, there aren't really any good explanations that I have at this moment of time, but perhaps the greater symmetry provides greater stability, if you want to call it like that, along which the information can flow. And counterintuitively, somewhat counterintuitively, this is perhaps a good thing. And and this is where I admit it becomes quite speculative, but these, I mean, as I said, these proteins are not completely unknown. I mean, it's not that we just discovered these PIK3 kinases. Those have been very well studied in many works. So here's a work that Dylan Wright did, Jack's student. So what he was doing, he was just knocking out random edges on one of these interaction graphs and recalculated the entropy. And huge loss along this way from a preclinical trial to an approved drug. And of course, that's also what makes these drugs so extremely expensive. Yes, so it's very meaningful to try to streamline this process and not to try just about anything, and then maybe one drug will come out a decade later. Here's what I would like to ask. What other mathematics have applications to biology and medicine, and other, I only mean not differential equations, dynamical systems, and stochastic processes. And I don't mean this in a bad way in any way. Of course, we all know that these are very useful, and we have seen many papers in this meeting which use those. But of course, we also all know that there's more to mathematics than just that. So I want to suggest group theory, or algebraic geometry, or differential geometry, or topology. And well, some of this is already being applied. So some of you may know about Simplers or security structures, and they have used algebraic geometry to study polynomial varieties which arise from chemical reaction networks, or also topology. I mean, if you know index theory or things like that. Yes, I just saw that.
Peter, Asner wants to do a partial differential equation, and I want
yeah, well, okay. I mean, I just would like to throw this into the room, and I hope I will see more and more mathematics, non-traditional, if you like, being applied to problems that originate in life sciences and biomedicine. So I would like to thank Janula Freeman, who gave us some good remarks. There was some funding to Jack, and again to Jan and his colleagues for all of us